Okay.
Hello, good day, good morning, good afternoon, wherever you are. Hello, everyone. Thank you for joining the GeoScience and GeoEnergy webinar of 28th of January, 2021, the fourth webinar of this year, I think, or third. Sebastian and myself are pleased and honored to host you all, and we wish you all are doing great. Students who are in exam period, all the best. I wish we could give some sort of exam questions from these webinars one day in our final exams as well. But nevertheless, please stay safe and happy. And as for the webinar of today, we are pleased and honored to welcome our dear colleague and friend, Sarah Gasda from Norway with us today. Sebastian from Heriot-Watt, Scotland, Sarah in Norway, Bergen, myself in Delft, Netherlands. So it's just all possible through this online technology. So quite impressive. I read a few lines about Sarah. Many of you already know her, but still it's nice to remind her about all the achievements she has achieved, or part of it at least. She joined a NORCE, Norwegian Research Center, in 2011. And previously was university research in Bergen as a senior researcher. And then in 2018, she was promoted to chief scientist. She holds a PhD in civil and environmental engineering from Princeton University in 2008. She worked with Mike Cilli, I guess, and I know that Mike was also our guest as well. So the two are good colleagues and friends. She was also awarded a postdoc position at the University of North Carolina, Department of Environmental Science and Engineering, which was funded by, the project was funded by KAUST. Her research and expertise is in computational methods and modeling of multiphase flow in porous media, with particular focus on geological CO2 storage. Over the past 20 years, her research has contributed to improving our understanding of long-term CO2 storage and contaminants, including the potential of leakage from legacy wells and faults, quite crucial and important topics. She has focused recently on understanding the role of pressure in larger-scale storage and seeking more efficient tools for appraising basin-scale regions for gigaton storage developments. She currently leads the research group in computational geosciences and modeling, a multidisciplinary group of about 12 permanent researchers and 3 postdocs and PhDs in one engineering, applied mathematics, physics, or computer science. So quite a diverse team that she is leading in North. The core of the research group that she leads centers around the Open Porous Media Initiative, OPM, a collaborative open source software development project, and the National IOR Center of Norway. The research group's project portfolio is focused within CCUS and IOR, but also includes smaller projects within medical technology, climate modeling, microplastic pollution, and geothermal energy. The group seeks to apply modeling and simulation expertise towards emerging applications within energy, climate, and environment. Please do visit her research page in Google Scholar, read her papers, publications, and contributions in the field, which are quite impactful. I just read a few more lines. I cannot do any justice to introduce her fully to you. She's just currently also serving as associate editor of the International Journal of Greenhouse Gas Control, IJGGC, since 2019. Don't remind her about the late reviewed articles or so in the questions and so on, please, which is a fantastic way to keep track of new developments in CCUS research. She's also in the editorial board of Petroleum Geoscience, with focus on application of geosciences to CO2 storage, energy storage, and the energy transition. It's our pleasure and honor to host you, Sarah. Thank you for graciously accepting our invitation. To the audience, please note Sarah's lecture will last for about half an hour, followed by questions. Please do type your questions in the chat box like always. And after the talk, Sebastian would chair the discussion session. And also, I noticed that we have also sent in the chat box the link to the Open Porous Media Initiative, quite a significant contribution in open science and open software development. Sara, we are all looking forward to hearing your talk, please.
Wow, thank you, Hadi. That was a very, very nice introduction, and I appreciate all the kind words, and I'm very honored to give this lecture, and very happy that you invited me, and yeah, I hope I get through quite a lot in about 30 minutes, I guess. I thought it was 35, so
it's
I'll
okay.
do it.
We can give you 35, don't worry.
That's okay. No, of course, shorter is often better, but anyway. Okay, so I'll just jump right into it. And of course, any talk about CO2 capture and storage at this point still, and I look forward to the day I don't have to have a slide like this. Do we need CO2 capture and storage? And of course, the answer is yes. And there are many reasons why CCS is a essential technology to help us tackle climate change. And I've listed up a couple of reasons of why we should think about CCS in a much broader perspective. First of all, really achieving zero emissions it will not be economical without multiple climate technologies, of which CCS is one. We may eventually, and probably will, have to go negative, meaning that we will capture CO2 directly from the air or using bioenergy to reduce CO2 concentrations in the atmosphere directly. CCS can be the cheapest alternative in a number of sectors outside of the power industry, which is where CCS originally started. Thinking about CO2 capture on coal-fired power, now we're moving much more towards process and waste industry that have a harder time reducing their emissions, switching to renewables. We can't think about access to energy without thinking about developing regions with abundant fossil fuels and what their solutions will be for them to transit just and fairly to a net zero future. And just to remind everybody about the average age of a coal plant in China is only 12 years with an additional 40 years of life. So this is very critical in the bridging from today's energy mix to something that we'll look forward to 50 years from now without coal. Okay, so CCS is really part and essential to the new IPCC scenarios that came out in 2018. I definitely encourage everybody to have a look through the report. There's lots of really interesting figures there. I just took out one where they have forecasted what the necessary amount of cumulative CO2 that will need to be stored in various scenarios, and I would just point to about three out of 4 of the IPCC scenarios rely on significant scale up of CCS, either in the zero emissions or negative emissions by the end of this century. So we really need to scale up from today's activity, where in 2017 we've cumulatively stored 0.2 gigatons, so 200 million tons of CO2, a significant number. But by 2050, IPCC thinks we should have 100 gigatons, so 100,000 million tons stored within the next 40 years. So it's a large challenge ahead of us. So current CCS facilities in the world, I mean, those of us who know a little bit about this know that there's been a tremendous amount of large, small-scale pilot demonstration projects all around the world. It's really good to see there's been a lot of experience gained through these projects. But just remind you that still only 200 million tons, despite all this activity, extremely important activity in a new industry, there's still quite a ways to go. Recently in Norway, if you don't follow local Norwegian news, Norway has the parliament has now approved, as of December, the first ever full-scale CCS project called Longship. It will be Norway's largest climate project ever, an enormous amount of public and private investment into this full-scale carbon capture, transport, and storage. The storage part is creating an onshore, it's called the Northern Lights. It's the transport and storage part of that Longship project. They will create an onshore storage hub that connects smaller capture projects to a large offshore storage reservoir. The very first capture project will be on a cement factory outside of Oslo. They'll be shipped around the southern coast of Norway to a terminal outside of, not too far from where I'm sitting right now, and then sent by pipeline out to the storage complex for permanent storage. So this is a project that they're already anticipating can be scaled up stepwise to include other sources and other maybe capture hubs other parts of Europe, other parts of Scandinavia. And so the team, the consortium of companies, a joint venture, Equinor, Shell, and Total, have already overdimensioned the initial installations for future growth. So this is what they're looking at in terms of potential areas to get what they call third-party CO2 streams sent to the Northern Lights storage site up here. And they've been signing lots of MOUs and various things. And here is sort of an overview of what their plan is. And you can see it's quite compressed. Within 10 years, they want to scale up from 1.5 to 20 million tons per year injection. Actually, they start at 500,000 tons. But very quickly ramping up that injection. But I'll just remind you that we would need scale up of, that would be equivalent to a scale up of about a gigaton stored within 50 years, 20 million tons per year. But we still would need 100 such large scale projects, Northern Lights, to really reach our IPCC milestone. So this is a good first step. We need more. Globally, we know that that maturing global CO2 storage at these scales is realistic in the sense that it's not outside of the scales of things we've already done. For example, hydrocarbon production. Philip Ringrose and Tip Meckel, and I guess you may have had, I think you've had a lecture by Philip Ringrose who probably went through this, have looked at if we take active wells in Texas or active wells in Norway, and we assume some things about what we can inject and injection rates and injectivity of these wells, that we could achieve in these couple of continental margins, gigaton storage with just a fraction of the wells, the global petroleum well that are there today and been drilled over the last 50, 100 years. So if you think about it from the point of scale up of infrastructure and going out and drilling, this is well within the reach of what we're capable of as a society. But their study also points to the fact that, to really look at and reduce the amount of uncertainty, we'll need to have dynamic simulations of these types of continental margins. These were done with quite simple, but still very insightful analytical calculations. Okay, so the big question when we're talking about scale up is really about the feasibility and about the safety. And the three main questions are, is there enough pore volume? Will it stay underground? And can we inject it fast enough? And we know the answer is yes to all three. We've demonstrated this at the small scale, but there are, and this is what I want to talk about, research challenges we face moving to this more climate relevant deployment of CO2 storage. Luckily, there's been a lot of thinking about this in the community, and there was a report published in 2017 by the so-called Mission Innovation. There was an experts workshop. I participated in one of the panels, and it came up with a set of priority research directions for storage and also for capture and for utilization. And I just point to three of these as examples of what the community sees, and I luckily happen to agree with all of it, of where we need to go in order to achieve and to facilitate this type of scale up. And it's all about multi-physics and multi-scale fluid flow, understanding pressure limits at the scales of injection, and also improving characterization of fault and fracture systems. And we can think about these three in terms of what it means really for large scale scaling up of CO2 storage. It's about pressure, it's about long-term migration and trapping, and I'll walk you through a little bit, but I just want to put this up here now. It's about unlocking new storage sites in different geological settings, because of the idea that a lot of the optimal sites will be used first, and we need to really build knowledge to help de-risk and make available more challenging sites as we see them today, and make them less challenging with new knowledge and data. It will be all about managing regional pressure buildup and sustaining long-term injection on these continental margins, and really making the most out of storage resources so that we aren't peppering the whole world with CO2 storage. We're trying to concentrate these into fewer regions and take advantage of economies of scale with regards to infrastructure and transport and other types of hub related issues. And ultimately, we need to be able to provide a convincing picture to stakeholders, investors, politicians that CO2 storage really is a low risk and effective climate technology at these scales, as we have done with the smaller scale. Okay, so we have a variety of storage settings. You can kind of categorize them, and this was a paper by Owen Tucker from Shell a couple of years ago. Actually, I think it's a book chapter, where, you know, if you think about it from choice A, choice B, choice C, and you hate to kind of put everything into categories, but let's just do it for the sake of thought exercise. If you take the first choice, and this is what I would call the conservative choice, of you have a structure, you have a trap, you fill it till it spills, or till, you know, you're happy that you filled it as much as you can, and then you're really reliant on the seal, and it's a contained system, and that's a very attractive system because you have it, you know where everything is all the time. Choice B is something that is, let's say, a different approach or a different type of geology, where you're relying on the migration of CO2 to store and trap the CO2 over the long term. And the scales here, of course, get much larger. Time and space increases dramatically, and uncertainty because of the scales then also increases comparably. And then you move into, let's say, more higher risk settings when it comes to induced seismicity or faults, where, you know, the trapping, it's still a structure and it's still similar in a way to choice A, but you have a more closed system, a more compartmentalized system, and pressure management may actually become more immediate concern there than in, for example, choice A and choice B. So, I mean, there are definitely advantages if you move forward to a gigaton scale that, you know, in choice A, capacity estimation is really straightforward. It's a volume of stuff, you know, that you're going to put in there. But in choice B, the global storage potential is really much larger for this type of migration-assisted storage. So at some point, we're going to have to live with, and there are already projects out there like Quest that are doing this type of storage. We're going to have to really enable our ability to tackle this type of potential with new ways of thinking, or at least different ways of presenting it. And then C is really about de-risking and understanding these systems. Faults are critical here to unlock these sites and make them available. So I don't need to talk to anybody probably here about CO2 and the system, multi-phase system, a few components. We inject CO2 as a supercritical phase to take advantage of the density. It's still less dense. It's still a buoyant phase and less viscous than the resonant flow. So you have things like gravity override and buoyancy that drive the system. Okay, so Gigaton challenge, how much can we get out of one trap? You know, it's really about how quickly can we inject, how much can the caprock tolerate. You know, this is sort of basic principles that, you know, the capillary seal of the caprock is really what's keeping CO2 there. You can look at, you know, very simple physics about the height of the plume, so the buoyancy pressure on that caprock, how much the capillary seal can tolerate. Getting down to the injectivity really, you know, starts at the pore scale to understand how these capillary pressure functions look like, and that will then enable us to understand how much flow we can get in there, in addition to the permeability, of course, at a rate that matches what's coming. How we can access all the available pore space, and how does the CO2 fill the trap over time. You know, here it's about capillary heterogeneity, it's about very small scale, but still potentially very important laminae and deformation bands, and all these things that will not, you know, will prevent access, you know, the CO2 being able to flow freely as it would in a homogeneous system. And there's been lots of really interesting work out there looking at how these quite small scale heterogeneities and capillarity can impact the larger scale behavior of CO2, even in a quite simple structural trap type of system. I mean, are there other processes that may help or hinder? You know, I have one slide on a PhD project. I did a lot of studying of long-term wettability alteration. Here we've seen experimental evidence that CO2 is, of course, we know is a reactive fluid, can alter the contact angle, which then has, and the time scales at which these happen, which can happen over, let's say, weeks to months. It's not an immediate change. So there's an exposure time element that actually changes capillary pressure from being whatever the initial wetting state to some maybe final wetting state. So we've done some work here trying to upscale these pore scale effects into capillary pressure and relative permeability functions that are dynamic, that are a function of the exposure time locally. And so that's been some really, really interesting work. And what we've seen when we've done some very simple simulations is that the long-term change in capillary pressure has an effect on the plume, that it makes it more compact. And that's, of course, CO2 will reduce its permeability as it changes from the non-wetting fluid to let's say, an intermediate wetting or more wetting to CO2, and it will fill the smaller pores and be able to move more slowly in the system. So that has an advantage for CO2, that you can get more CO2, but it also could reduce the amount of residual trapping, things we haven't really investigated yet. It could also reduce the effectiveness of the seal, because the capillary seal is really dependent on CO2 being a non-wetting phase. But in another way of thinking about it is that, well, okay, if CO2 is seeping up into a caprock, who cares? Because the caprock has nanodarcy permeability. So all these things are kind of part and parcel of things that we need to start looking at, especially moving to larger scales. Okay, there's a lot of other things we can talk about structural geology, how that affects flow, how caprock heterogeneity itself and roughness in the caprock, it's not a perfectly smooth surface, how that affects the CO2 migration. There's been a lot of work done. I just point to a couple of things I've been involved in, of course, but it's these types of behaviors at the heterogeneity at all scales that are affecting how CO2 is moving. And I think the point of this is that if you are relying on migration up dip to be your main form of trapping mechanisms, then you have to understand even how small scale things are affecting the large scale behavior. And then finally, this is, of course, there's work done on the dissolution and convective dissolution, and there's work done on understanding what the residual trapping is, how to quantify the trapping models. And again, the point here is that we can do these at the very small scale. We can look at core flooding. We can look at CO2 dissolving in brine in the lab. And then the question is, again, when you move to big structural traps, very large scale migration-assisted storage, how are these and the uncertainty built into these processes really playing a role? So it all comes together in a plot like this, which is a quite famous plot from the IPCC report in 2005. It's still still really prevalent because it still applies all the time, that structural and stratigraphic trapping are the main trapping mechanism for, let's say, the operational phase of the storage site. And over time, residual and solubility trapping take over. And I'll just note that for many systems, the mineral trapping is a long-term and secondary effect, but there are some highly reactive systems, such as volcanic rocks and basalts, that can fix CO2 in mineral form in very short timescales. And I don't talk about that here, but just so that everybody's aware. Okay, so how these are all put together, this was a study, again, going back a couple of years, but it's still really important to point out that when you inject CO2 at climate-relevant scales, and this is an example of the Hansen study we did a number of years ago, it turns out that the same formation is now the Northern Lights storage site, but this is well before we knew that, or anybody knew that. This is not at all, just to point out, this is not at all a simulation of the Northern Lights. This is just an example of how when you inject CO2 at large injection rates, 4 million tons a year, this coupling of capillarity, transport, structural trapping, residual trapping, and dissolution, how they all work together. So you can see that the CO2 is a mobile phase, and CO2 trapped residually and CO2 trapped as a dissolved phase. They lie on top of each other because you still have mobile CO2 that's trapped in the very fine scale things you can't see. And it also is trapped by its own limitation, its own relative permeability. So it's moving so slowly, it's essentially stopped. And the point of this is that everything is large. The tens and tens of kilometers, these are 60 by 60 kilometers, and the CO2 is moving extremely slowly, 10 to 15 kilometers every 1,000 years, right? The nice result is that it's compact. If you think about it from a monitoring point of view, you don't have to monitor 60 kilometers. You just need to monitor the few kilometers around, and that's certainly within the abilities of current monitoring technology. If we look at how it distributes, This is that IPCC figure now quantified for this particular set of parameters. And 95% of the trapping is provided by the cap rock in the first 100 years. So as much and important as residual and dissolved trapping is, it's the structure and the cap rock that does the job before this gets handed off. From the storage operator's point of view, it's the structure. But what can be learned in the first 50 years to narrow down the future uncertainty? And the uncertainty comes again from these very fine scale things that will the compartmentalization means the CO2 doesn't move as far, means you get less dissolution, more dependent. So there's the interplay of these things is really important to explore, and we haven't gotten there yet. We know we have an instinct, but I don't know of anybody who's simulating the impact of lamina and deformation bands at these large scales. The same with lens residual trapping. That will have an impact on the plume extent, more or less contact with new brine, more or less residual trapping. And the same thing with convective mixing. If there are any baffles, if there are any types of fine scale laminae there, deformation bands, what have you, that will also reduce convection and reduce the amount of dissolution you're getting. And then put more reliance on the residual and structural trapping overall. Okay, I only have a little bit of time, so the role of pressure, of course, as we have evolved as a community, we've known storage from the trapping and migration point of view is really important. Pressure is equally important, and depending on what the system is what you'll need to pay most attention to. This is a great figure from Johnny Rutgers going back a few years, still applies lots of ways things can move and crack in the subsurface. That looks very scary, of course, but it's certainly we believe that we can manage this so that we don't get injectivity problems, we don't reactivate faults fractures, and we don't induce seismicity that would be felt seismicity. But the question is how we do that. How we determine maximum pressure is a big portion here. I won't go into this. It's there's still a lot of uncertainty of what the maximum pressure really is that you can tolerate. That you need to do extensive testing. There's a lot of variation, and then when it comes to fault stability, for example, predicting the actual pressure at the fault, even if you have, let's say, you accept more column as a very simple but still relevant analysis, understanding what will effective stress look like at the fault is still, I think, an open question. If a fracture happens, we can try and stop it. This is work we're doing on microbially induced calcite precipitation, looking at ways to target cementation, in situ cementation, so that you could block leaks if you find out that they're happening. I'll point to the paper there. Okay, so sustained injectivity is really the issue as you move from single site to multi-site injection. This is a nice figure from Zhu et al. From 2008. Talking about how different types of systems affect how pressure will evolve, and the bottom line is that in closed and semi-closed systems, which of course real systems are somewhere in between open, closed, or semi-closed, you will have to actively manage the pressure sooner or later, and this of course can apply to even an open system if you really are injecting at very high rates. This type of pressure management has been studied. This couple here from the Illinois basin, I don't have time to go through the details, but just so that if you're not aware that these are things that that the community's been thinking about. It presents another challenges because now it's about the scale and the boundaries and the far field and how the seepage through a cap rock over hundreds of thousands of square kilometers is affecting the pressurization, how a far field boundary, which you may not know if it's open or closed, how that affects things. And really secondary is the plumes themselves. And in a lot of cases, there's not a lot of focus on what happens to the CO2. The focus is on the pressure, which is completely understandable. But if you have systems where you need to know the CO2, and this is another nice study from Carl Bandilla and Mike Celia a couple years back on active pressure management and how to target it, but still raise another important issue: what to do with the produced water. In Norway, in the North Sea, we've done a lot of studies, and here it's I don't actually not so familiar with Illinois Basin in terms of the range of capacity, but I think everybody's mostly agreeing for the Utsira that nobody agrees of what the capacity is of the Utsira, which is, by the way, where the Sleipner CCS, which is a very small, no pressure impacts of Sleipner right now. But it's like you scale up Sleipner by 100 times. Nobody agrees on what the capacity is yet, because it depends on whether you have closed boundaries, whether you are doing water management, whether you're depending on uplift of the compressibility of the system to allow the system to pressurize more. So the orders of magnitude of variation of the capacity of the Utsira still to this day. I guess I have a few more minutes. I can't actually see anybody, but somebody will shout if I need to
Yes,
stop.
absolutely. No, you please go ahead. You
5 more minutes or so?
5 more minutes. Absolutely.
Okay. Yeah, so the point is that these are studies that are looking at tremendous scales. Here, I didn't actually point out, this is the scale here, the bar is 200 kilometers. This is just, so this is about 400 by whatever, 600 kilometers. The Utsira is 100 in width and going into 100, 200, 300, 400. So enormous scales. So the expectation right now that you can, there's no way that any of these studies and that nobody has been able to do everything all at once, either focus on pressure and not CO2, or CO2 migration and not pressure. It's hard to do both. And there's let's say conventional thinking is the wrong way of saying it, but the CO2 will be injected, and you really just need to have the vault. You need to know where the CO2 is. You need to know its properties, but you don't necessarily need to know the intricate details of where it's moving in order to get these very large scale pressure. This is showing, these are all, by the way, CO2 plumes. Here is actually showing you pressure. So the impact of the very local behavior of the plume on the very large scale pressure is more or less thought to be decoupled. Now, you just need to get the CO2 in there with its properties. It has a compressibility that has a role to play. But after that, then everything is really about how the pressure is dissipating around, and not so much how the CO2 is migrating. This was actually a case where that's not the case. This is again the Utsira, but a bit. This Utsira is actually connected to another formation underneath it. It's actually the Gasda Utsira aquifer system, and they're separated by a relatively thin large shale barrier, but that has an end. And so they are connected hydraulically, although that's still up for debate, geologists and things like this. But I think it's so if you were to inject CO2 into the underneath the Utsira and use the Utsira as a kind of pressure release, you can do quite a lot of injection into the Gasda. Here, these were looking at different scenarios of different compressibilities and permeabilities, and you could get 50 years of injection without any kind of pressure impacts. But if you let the system now, you shut off injection and you let the system now reach the CO2 reach and stabilize itself, what happens is the CO2 eventually finds its way to this white line, which is the edge of the separation between these two aquifers. And just like if you just put water on a table and it were to spill off the edge, CO2 spills upwards over the edge and ends up in the Utsira, crossing over a couple hundred meters of vertical depth, and expands and actually creates a pressure, reduces the effective stress and creates a pressure problem in the Utsira some hundreds of years down the road. We can debate whether or not you might care about that, but the point is that in this case, you need to understand the details of the migration. You need to understand, these weren't done, by the way, with any kind of dissolution trapping, just to show that at this point now, these things are more tightly coupled. And when you go farther down the line, whereas CO2 ending up somewhere will have an impact on the pressure sustained, what that particular region can sustain in terms of pressure increase. So it's just pointing out the complexity is needed in certain situations in the models that you're running. Okay. Okay, just a couple more slides about some other aspects about pressure propagation. So many of the studies that were done were on these large scales are using average permeability and porosity, because that's usually the best you have, or at least as good as you can get it. If you were to hypothetically start to play with systems, and this again is the Utsira starting to play a little bit more with hypothetical again, permeability variation, and these are two variograms that are just changing the angle of the heterogeneity, and run the simulations. Inject hundreds of millions of tons a year, and now understand what is the capacity by just very simply saying the time, how much injection, how many years can you inject until some pressure limit somewhere in the system is reached. In Utsira, the case is that the pressure limit is reached first, not where you're injecting, but at a farther location where it's shallower, and the window to that you have in shallower regions is smaller than you have in deeper regions. Point is that no matter what you did with the angle, your estimated mean, and this is a probability distribution of time to pressure limit is reached, is around 52 years plus or minus, no matter what the angle is. So there's a lot of overlap in these two PDFs. A little bit different, but still a tremendous amount of overlap if you were to stretch these things and make them larger. Again, the mean is still very close to itself, even though the shape of the distribution changes. So there's not a lot of variance, no matter what kind of heterogeneity you test. And the reason for this is because it's a very high permeability system. But as you move to a lower permeability system, now your estimated time to capacity, let's say, proxy for capacity, increases by 50 years. And the spread is much larger. And so the point is that depending on the sort of background mean, the impact of heterogeneity will be different. And what was surprising was that the mean, well, let's say not surprising when you think about it, the mean time you could inject increased by double. And that's just because that permeability is lower, the pressure pulse moves slower, and the how long it takes before it reaches the sensitive area, which is 100 kilometers away, takes longer. So you can get more CO2 in. But the other thing about this is that these were done using very standard Monte Carlo. In order to get a fairly good estimate of the mean, we had to run 400,000 samples. So the question is really about understanding uncertainty and how well we can do that, and the types of simulations we need. These were not run with Eclipse 300. These were run with a very simple upscaled vertical equilibrium model. And so then we could achieve 400,000 simulations in a short period of time, which is not the case if you were doing something more complex, if you had to worry about CO2 trapping and other types of things. Okay, so I'll just stop. I think the real challenges for us in the modeling simulation community is really tackling these large scale simulations, at least having the ability when needed to bring up scales, small scale behavior to the large scale. And right now we are very limited in what we can tackle at these very large scales. Grid blocks, I'll remind you, are on the order of kilometers. I gave this talk to Imperial College last week, and I put up a picture of Hyde Park, Kensington Gardens in London, to put a picture on the scale of these grid blocks, enormous grid blocks. So we have to do a lot more subscale understanding and subscale upscaling, or other ways of incorporating fine scale information at these very large scales. So I think I'll stop there, and thank you very much, Hadi and Sebastian, and take questions. I put up my summary outlook, but people can read it while I...
No, but thank you very much. It was very, very engaging and inspiring talk. You covered all the important aspects, and I would expect a lot of questions to come. So, Sebastian, it's...
Yes, thank you very much, Hadi. Thank you, Sarah, for great talk. We already have some first questions coming in. I'm going to use my privilege as the moderator for a minute here and pick up on something that Hadi mentioned, commented on in the beginning. You work on the open porous media initiative. So what are the advantages of using such a community tool to tackle and understand, optimize CO2 injection? And on the other hand, given the scales that you had in your second to last slide, what are the current simulators that industry has released just simply too limited in making reliable CO2 injection prediction with CO2 injection?
That's a very good question. I skipped over this. Skipped over the slide. So first of all, I just want to say that, and I did have another slide here. For many cases, and especially these conservative, I wouldn't say conservative. Okay, we'll call it a conservative choice. But the structural traps, because the size is limited, you can, and they do 3D classic reservoir simulation with Eclipse or whatever your favorite simulator is. Shell has their in-house. That is perfectly acceptable. There are very few systems that have gone to these very large scales. There are some migration assisted, but so if a smaller scale, you can use standard reservoir simulation, especially of the operational time scale when it's really the multi-phase flow and there's not much to do with convective dissolution and stuff. But okay, but the question about OPM and why OPM and why another simulator, I think it's two things. First, yeah, the openness it's not a challenge to the commercial simulator. I mean, that's fine to make money. But I think openness, especially when we're talking about a societal challenge and, community codes and transparency are all, I mean, open publication, open access, in the movement towards openness. And OPM has been around for a long time as an open source simulator dedicated more towards oil and gas reservoir simulation. And what we saw is I think what a lot of are seeing is that, if you're going to create community code, first you need to do two things. First, it needs to be usable by industry. And that OPM does is that it can take standard Eclipse, industry support, basically, the traditional industry ways of working, their workflows. So we do that at the same time as high-level cutting-edge research. Not to say that Eclipse and Schlumberger don't do that, but we have, team of mathematicians and computer scientists, a smaller, more agile team that can take in the newest, latest, greatest, technology of the numerics and adaptive griddy, whatever it is. The second thing I want to say is that, CO2 storage has used now, especially the operators have used Eclipse and used CMG or their in-house. And if we're going to move towards CO2 storage being its own industry, then we need our own simulators. Hacking and massaging oil and gas simulators into a CO2 storage simulator will only take you so far. And it works pretty well so far. But I think as we move into 10 years down the road, 20 years down the road, the demand for dedicated simulators for CO2 storage there's lots of good simulators out there, Stuttgart and Stanford, but the ones that are, let's say, more happily used by industry will be in demand. We'll need lots of types of simulators, I think. But that's our philosophy and our vision for OPM, is to bridge the gap between research and industry. And we're not the only ones trying that.
Sebastian, would you allow me now to use also my ticket?
Of course.
Following up what Sebastian mentioned, so you welcome the audience to actually contact and reach you for merging their work and join the community. Would that be also a possibility?
Absolutely, yeah. I mean, I didn't put up the GitHub, but it's available for download on GitHub. It's an open, anybody can contribute. The major contributors are Equinor, Sintef, NORCE. We have a new project supported by Gasda, which is
fantastic.
Good. But I mean, we have contributors from TNO in the Netherlands, from all around the world. So it's
Yeah, I knew the answer. I wanted the audience also hear it, that they are most welcome to join. Yeah. Thanks, Sebastian.
Okay, now let's go over to the questions from the audience. And the first one is from Vegeta, who asks, are there any disadvantages of injecting or storing CO2 in rocks that have already been studied? And I assume, Vegeta, what you mean here is stuff in rocks, in depleted gas reservoirs, for example. So where we know more about geology because we have taken fluids out in the past.
Yeah, no, it's that is, I did not mention that. That is another area of very active development, especially in the Dutch North Sea, of converting depleted gas reservoirs to CO2 stores. Are the advantages and disadvantages? Yeah, the advantages are, of course, we know more about how the system behaves. The disadvantages, if it's an oil reservoir, then you don't have issues of pressure depletion as you do for gas. But gas reservoirs that have been severely depleted introduces a new set of challenges with regard to Joule-Thomson effects, and everything gets more complex. Of course, you have hydrocarbons you have to think about, so your modeling and simulation becomes more complex. And the other thing you have in depleted are a lot more legacy wells, which, of course, you probably know a lot about because they were recently used, but it's still, that would be the main risk. It's a manageable risk probably, but the main risk is that you have now a very well punctured previously producing hydrocarbon reservoir. So those are the disadvantages, one could say, but it's not insurmountable by any stretch of the imagination. It's a good question.
Thank you. Yuang has a two-part question, and I'll start with the first one. Thanking you for the great talk. Could you explain the time-dependent wettability change? Is there any experimental observation? Was it mainly modeling? Sorry. And the second part of the question is, how would this wettability change then affect relative permeability?
Yeah, I flew through like I said, it's a 3-year PhD, 4-year PhD in one slide. There are, we did not do it, but there are experimental. So this is actually, this picture here is an experiment done by Tetsu Tokunaga at LBNL, where they were doing some CO2 core flooding in carbonate sands and other types of sand. And they observed contact angle change over the period of 6 months. If you go into our papers, you can find the paper. We did a modeling study because that's what we do. But what we found was that we need more experiments. So the modeling study we did was upscaling from pore scale to core scale, where we pinned the core scale dynamics or the Darcy scale dynamics back to this pore scale alteration. And then the question is, what does the pore scale alteration really look like? And that is not a lot out there, but there are some data, but it's very limited because usually it was a side effect of something else that they were doing. No one has really studied this in great detail with experimental work. How it affects relative permeability, this plot here is showing, this is the wetting or the CO2 phase relative permeability. You get a shift in the pore filling, right? So rel perm will move, a CO non-wetting phase will move from primarily filling the large pores and having higher relative permeability for given saturation to primarily filling the smaller pores as it becomes the wetting phase or more wetting. So that will reduce its relative permeability, and vice versa for the water that's there. So you'll get a kind of a shift in one, your rel perm goes down and the other goes up. Generally speaking, for simple pore scale, this needs to be studied with more complex models, but this was generally, this was the first order effect. I hope that answers the question.
Thank you. You'd spoken about grid blocks of the size of Kensington Gardens. It was Kensington Gardens Hyde Park in London. Hyde Park, which is quite significant. So Zhao Kong wonders, again, thanking you for an excellent talk. One question about CO2 dissolution in large simulations. What kind of grid block size do you use to capture CO2 fingers, and how about the simulation time? So the one Hyde Park grid block is probably too large. So how many
too large
garden-sized grid blocks do we need?
You would need, each individual rose in the garden would need to be its own grid block. something like that.
Mm.
Yeah, centimeters to maybe meters. It depends. There's been a lot of work done on these the scaling. So it scales with permeability, porosity, diffusion, and missing. Oh, and the density change, which is relatively small. So yeah, roses to bushes.
This was the best answer I've ever heard about the grid resolution impact.
So, Hadi, when your students in the future answer, what is the optimal grid resolution? 1 rose?
One rose or
That's
a bush.
100% in Hadi's exams.
No, but in the simulation times, I mean, so we don't want to know. I mean, so I think, didn't Maria Lanius and Hamdi Chalepi, they did do this with GPRS. I don't know what their simulation times were. If Hamdi's here, he can say. But it's way too long. So we need to upscale, and there's lots of ways of doing that. There's lots of literature on upscaling these fingers into something more manageable at the Kensington Gardens scale. I just didn't talk about this here.
Okay, thank you.
Mm-hmm.
Soren has a question. Again, thanking you for a motivating talk. Are the choices A and B in the storage settings that you've shown conflicting? B relies on the system's long-term behavior. At this scale, the C and A may become permeable.
I mean, conflicting. I guess what would be why conflicting? So they are not. Yeah, they are not same. They have different characteristics and different ways of approaching how you store. Are they conflicting? No, because I think in many systems you're going to have, if you're going to do, let's say, 10 different sites offshore Norway around Northern Lights, you're going to have a mix of storage that will be in structural traps and storage that will be in this more long-term migration behavior. And they're in conflict. I guess I don't understand what Soren means by conflict.
He says that you need to be you're waiting for or you're looking at the long-term behavior, and then given the long-term you may have in A, you could have some chemical reactions happening in the overburden that may create additional flow paths, etc., and leakage paths. Yeah,
that's true. I mean, I think if you go back to the keeping CO2 in a structural trap, meaning you're keeping CO2 as a unstable phase forever. But we have lots of examples, Soren, of that natural CO2 reservoirs in the US where we know CO2 can be kept under a seal for geologic time. So it's just a matter of what is available to you where. I think that's really the point. And if you had a structural trap, you maybe pick that one over the migration storage assisted trapping, migration assisted storage, but that may not be the case. I mean, I think it's very much dependent on the geology and where you are and what you have available, what you're going to choose. I just think that from what I've seen so far is that the first choice are these structural traps because they are an easier sell. You don't have CO2 that's just going to kind of go everywhere for thousands of years. It just sits there. Everybody's happy. We understand it. We know the capacity. It's less uncertainty, I think. But yeah, it's a good question.
I'm going to jump down a few questions just so we can continue a little bit on that topic. Charles asks, hi Sarah, quick question. Currently, most planned CCS sites are located offshore. Can, and if yes, how, improved modeling help with developing onshore CCS? Or do you expect offshore to stay dominant? You just mentioned examples, onshore examples where CO2 has stayed in place for times.
Yeah. Well, let's say Europe has much more comfortable with offshore, or at least as far as they're comfortable with CCS in general. Offshore seems to be the choice because it's not in my backyard. And there's a lot more issues with onshore public acceptance and other societal issues, although I think those can be eventually surmounted, but probably in a different way than it's been done so far in Europe, which has been to meet massive public resistance and not get anywhere. But there are good examples of onshore storage or at least pilots. The Ketzin site in Germany was a wide success, and the local community thought it was great. So I mean, whereas in the U.S., you know, onshore oil and gas production, I guess the question is really, I think we foresee everything happening, both onshore and offshore. And again, it's not even just about the geology, it's about the local geopolitics and you know, there's many more factors than just what is the right technical solution. You have to find the right technical solution that matches the local society and the people who are there. So
and
there's
you need
no
the CO2 sources nearby as well.
Well, I mean, if you look at the Northern Lights model, the CO2 source will be in Sweden, and the storage site will be in Norway. And there have been some surveys now done by some of my colleagues here on what is the perception of CO2 that is domestically produced CO2 being stored offshore, and what is the perception of CO2 coming from Germany and being stored offshore. And people are more favorable to their own CO2 being stored offshore than foreign emissions. But I mean, the whole Northern Lights model is built around foreign emissions coming to Norway, because Norway's local emissions are minute compared to the rest of Europe. So I guess the point is that there has to be a larger conversation about the sources, the sinks, what our climate objectives are, and how people feel. Yeah, there's no one size fits all, and so there's a lot of work that needs to go into every single site about building up this multi-dimensional framework around, we're going to do this, and get people on board. But yeah, it's easier offshore than onshore because it's located farther away, and yeah, a lot of complex things in that question. I don't know if I it.
Interestingly, so there was a question. I don't think you need to answer this, because Johan asked the question for proper site selection. What are the main parameters we think we need to consider and include in certain quantification studies? And I think you answered that it's just much more than just the geology. It's politics, where does CO2 come from, etc.
Yeah, it's finding the right match, and it's, you know, some sites may be much more straightforward. You know, there wasn't any discussion about, you know, Schleipner when they started injecting CO2, but it was really when it became the full chain and that it became a discussion. So yeah, so it's not just technical, and the same thing goes for monitoring. You know what? I didn't talk at all about monitoring, but when monitoring is an essential component to public acceptance, right? But it's also an essential component to many other things. And what you need to monitor from the technical point of view, and what you need to monitor to bring people together that this is the right thing to do, are usually, or let's say they're not always coinciding. There's an overlap there, but you might have to do extra monitoring to convince the local population than you really believe is necessary from the technical risk, right? And that's okay. I think we should live with that.
You mentioned monitoring, and so we're running out of time, but there are a couple of questions that we can perhaps just get through quickly. So Ramin, also thanks you for a nice talk. In addition to monitoring the CO2 movement, have you tried to determine CO2 trapping in situ? Are there any efficient ways to do this at such large scales?
Yeah, I have not personally tried to determine CO2 trapping in situ. There have been some pilots, the one in Heriot in Israel, where they've tried to do some quantification of in situ residual trapping. I haven't followed the latest there, but so I mean, at large scales, I don't think there will be any expectation that we'll be able to monitor the trapping. You know, I think monitoring is we'll be able to monitor the plume, then we can deduce what is trapped, and that's been done at Schleipner, for example. They've taken a combination of gravity monitoring and seismic, and have estimated in a number between 0 and 20 could be 0, could be 20 kilograms per square meter dissolved per year from the Schleifner injection. So they can put an upper bound on it. I think that's as much as we will ever get. Like, I don't think you're going to go drill a well in Schleifner and measure the dissolved CO2. It's just you're adding costs and you're adding things. At some point, I think back in another one of my slides, it was, all the residual trapping and solubility trapping are going to happen hundreds of years after the project has completed. So really the question is, what can we learn in the first 50 years or 20 years to say something about how well this system will stabilize if you're depending on that for storage? And then at some point you have to hand it over back to society or back to whoever. The storage operator will not follow that project for 1,000 years. So it's a question of trying to put some bounds on things now, and we can refine those uncertainty bounds as we move forward. And so by the time you close the site and maybe have to monitor, you want to try and build a case for not monitoring very long after the project is completed. And that I think is still an exercise that we need to think more about, the post-closure handoff and how that will happen.
I'll take one last question here, because you talked about the long-term effects, and Leila, again, thank you for the great talk. And wonders, is there a way to enhance the mineral trapping, because that's really
the most permanent. Yeah. I mentioned the basalts, the carbon fix project in Iceland, where they are demonstrating today that you can fix CO2 as a mineral phase. So you need to have reactive minerals. Can you enhance that? I'm not sure if you necessarily would want to, because when you start to change the mineralogy and dissolve and precipitate things, you could potentially change the permeability in an adverse way and impact your injectivity. So I don't know if you can, let's say, but I don't know if you'd want to. I think that's really my message there. That we'd have to think about very carefully. And this calcite precipitation thing that we're doing, it's a modeling study, but there are also you can get calcite precipitation by use of microbes. You can get that fairly quickly. But again, it's really a question of how to control that precipitation so that you're not creating another problem, plugging things up where you don't want it to be plugged. So yeah, it's a good question.
Thank you much, Sarah, for great talk, for taking the time to answer the questions from the audience and from Hadi and myself. And apologies to thank you to the audience for the excellent questions. Apologies if you couldn't put all the questions forward, but time is up, so I need to hand over to Hadi for some final comments. Thank you again, Sarah.
Thank you very much. Thanks to the audience as well for the nice questions. I'd like to quickly take the chance and introduce our next week speaker. We are going to host Professor Zuleyma Karpin from the Penn State, and she's going to give a lecture about in situ contact angle measurements and weathability alteration in porous media. So stay tuned until next week. Stay happy, healthy, and tuned at the same time as always, 4 p.m. Central European, 3 p.m. British time, 7 a.m. California. Now I'm becoming like airport announcement. Stay safe, happy, and please, travel with us. Yeah. So we see you next week. Sarah, thanks a lot. That was really an amazing talk.